All right, let's get started. Um, Hello, everybody. Welcome to our next round of IRIS-HEP Fellows Lightning Talks. Um, First up today, we have Nishank.
Um, okay, hi everyone. Yeah, so my name is Nishank. I'm doing my project over the summer on towards differentiable jet clustering, working with Annalena Koffler, Nicole Hartman, Michael Kagan, and Lucas Heinrich. So yeah, we can just get started. So the agenda, right? So what should we cover? So we'll talk a little bit about, what is jet clustering? What are the problems that we currently face? Our motivations as to why we're doing this project in the first place. Some solutions to it, so like optimization, why we're, what we can do to fix the problems that we're facing, and some applications of our solutions that we're going to find. So yeah, let's just get started, right? So what is jet clustering? So to start with jet clustering, you kind of need to know what jets are. So jets are basically just columnar sprays of particles that, occurs via hadronization. So if you have a particle collision, you get this cascade of decays, or you get this cascade of like you get a single decay, and then from unstable particles, you decay to, you know, another set of particles, and you continue this huge cascade of decays until eventually you come to stable particles, right? So inside of, for example, like an atlas or like a tracking detector, you have something that, it's capable of detecting your stable particles, right? So your EM calorimeters, your muon reconstruction chambers, etc. So the way jet clustering works is it's an iterative process using parameters like your distance, your angular ordering, your momenta, all these things, right? Based off that, you create these little subjets, and then based on how you combine it, you can create this jet, right? So this jet is important because it can tell you about the invariant mass of the particle. It can tell you a bunch of details about the original particle that it came from. So, all these words, but maybe you should see a little picture, right? So here's an example, right? So if you have a proton-proton collision, like something or a PV collision that's happening like in the LHC, right? Um, you have, parton showers, you have fragmentation, and then you have hadronization, right? And then eventually, after this whole process, you have this whole branching process, and you'll create stable particles that you see at the very top right. And that's what the detection is, right? So in this case, like the darker the square, you have a higher momentum particle, so you have a harder particle, right? So uh, the idea is you're going to cluster around higher particles, and the idea is basically you want to find out the original particle that your huge, cascade of decays came from, right? So let's say that create your algorithm creates these two little subclusters, or subjets in this case, right? Basically, the way that your algorithm works is it creates decisions on whether you should merge or you should not merge based off all the other information around it, right? So you have these little subjets that are being created around these higher momentum particles that have been detected. So once you create these two little subjects, your algorithm decides should we merge these or should we not merge these? And that depends on the radius r and the features of what you have, right? So in this case, if you merge it together, you get this huge cone, right? So this is basically going to be what your jet is. So this goes all the way back down to one particle if you look on the left side, right? So this is basically how you tag something. So this is how you determine this is a bottom, like a B jet or a C jet, right? So it came like your whole cascade of decays, all the stable particles you have on the right, all initially came from this one particle from the left, at least in this example, right? So that's just like a, you know, picture, but here's more of a actual physics example of what, a hadronization, like tree branching structure would look like, right? So you have an electron-positron collision, interaction via Z boson and Z or a gamma. And then you have basically this huge cluster of decays that can occur, right? And then it decays all the way down to where you have stable particles. And then you'd use those stable particles to reconstruct pseudojets or subjets, and then you use those subject clustering to find the full jet, right? So what's the problem with jet clustering right now, right? So jet clustering, one of the issues that, typically when we do jet clustering, we just have one free parameter of R and you usually just optimize it at the very start and then you don't re-optimize it again, right? So you just make the radius equal to 0.7, right? The problem is your jets aren't always going to have the same radius. If you have higher momentum jets, you expect smaller radius. If you have lower momentum jets, you expect, a fatter or wider jet, right? So your radius isn't necessarily always going to be the same. So just having one constant value for it doesn't necessarily make the most sense. On top of that, so clustering itself, when you have these little subclusters, so if you look at this, right, you have two different subjets and your decision to merge or not merge, right? So in this case, you merged it together into one jet. That decision to merge is a probabilistically it's just a binary decision. It's either you merge or you don't merge. So in that case, you can model it as a step function on the right? So this step function has 0 or 1. You can imagine that 0 is a not merge decision and 1 is a merge decision, right? So given a bunch of subjects, you have to decide whether to merge or not merge. But the problem is this decision that you make is not a differentiable decision because this function is inherently not differentiable. It creates the delta function when you take the derivative of it, right? So how do we solve this issue? What do we do to fix it? So you want to make it continuous, right? You want to make it something that's, more readily differentiable. So that's where you can use a sigmoid function. So in this case, this function is 1 over 1 plus e to the negative at. The idea is if you increase a to a much higher value, this function approaches the step function almost perfectly, right? The benefit is that this also gives you a smooth probability distribution, and you can now take derivatives of this. So you can use this for jet radii calculations. So like if you use if you can pass back with differentiability in your jets, you can basically reconstruct you can determine like the optimal radius essentially, right? So on the right there's this little plot of the dijet invariant mass reconstruction. So the idea is that the resonance widths vary with differing radii for the anti-KT algorithm. So if you basically if you were in our ideal case, you could take a derivative and determine this optimum instead of having to iterate through all the different R values and determine the optimum is manually, right? So derivatives are basically speed, like it makes this process significantly more efficient and in terms it allows you to determine a variable R uh, more effectively. So yeah, um, the idea is introducing differentiability into jets is really important because that's one of the core issues with, using machine learning for jet clustering. The idea that jet merge decisions are non-differentiable, so you can't necessarily use, automatic differentiation or backpropagation. So if we did have differentiable jets, you could do backpropagation, especially in the context of neural networks, right? So you can, so currently we have, machine learning algorithms for jet tagging, but you can lump some jet clustering, jet tagging together, and subjet clustering, right? So this allows you to basically determine information about the particle decay, and you can, start tagging B jets, C jets, combine the whole thing into one, which is something that we'd want to do. Um, yeah, but those are all the applications of it. I think that should be about the end. Yeah. Okay. Thank you so much for listening. Really appreciate your time. Thank you.
Thank you, Nishank. Any questions for Nishank? No. Thanks again. Um,
Thank you.
sorry. Up next is Maksym.
Yep. Hello.
Hi.
Just a second.
Sure.
Okay, so I think, yeah, please let me know if you see the presentation.
Yeah, you're all set. Go ahead.
Yep, nice, thanks. So, hello everyone. My name is Maksym Andriichuk. I'm from Kiev, Ukraine, And I will be presenting you my project, which is optimizing automatic differentiation using activity analysis. First, I'll have to tell you a bit about CLAD. CLAD is a Clang plugin for C++ mathematical functions. So basically, the way it works is it analyzes asymptotic syntax tree, which is created by Clang, and just makes the derivative code available. So we have a square function, which is just basically a function that represents x squared. And we can see that every operation is somehow is in a syntax tree, so we can use it to somehow create derivative of that particular code. So what is activity analysis and why do we need it? So here's a bit of a motivation behind the activity analysis. Let's just jump straight to the example. Let's say we have a function f from 3 variables. And basically, if you take a closer look, what it does, it just returns a times b. So that's it. And if we want to differentiate it with respect to a, we get the code here. And we can see that some statements are not in fact needed. There are some excess statements, like we don't need to create an adjoint of variable d, since it just doesn't, it's not needed in a computation of the final derivative of x. So the way we want it to work is here. We don't have adjoint, we don't create adjoint for c, and we don't create adjoint for d. The way we do it is we'll basically mark variables as passive or active. In this particular example, we'll have that d is a passive variable since it just doesn't, it's not needed for a computation of x. And we'll call in variable active if it is needed. So in this particular example, we'll have that a is active variable, x is active variable, and b is active variable, and all other variables such as d and c are not. So the way we'll do it is we'll create variables, two variable sets. First one is varied, and second one is useful. Basically, varied set of variables are the variables that depend on some independent inputs, such as a in our first example, and useful set of variables that somehow influence the dependent variables. So again, in our example, we'll have that d is a useful variable since it is influenced by variable a, but it is not varied since it is so it's not varied. So the way we'll do it, the way we need to find those sets is kind of really naive. We just basically use some like really natural relations of depends in a differentiable way, and we get the following relations, which I won't really get into. Again, they're kind of obvious and really natural. And at the very end, we'll say that the variable is active if it is both varied and useful. So let's compare. So currently, CLAD works not as efficient as we want to, and it is represented by the red graph. After the release of active analysis, it would significantly improve, and our ultimate goal is to basically make CLAD work as good as manual. So just to note, there are many already implemented analysis in CLAD, such as TBR analysis. It is also somewhat similar to activity analysis, and the ultimate goal is basically to make TBR analysis profit from activity analysis. And I will be doing that, and I guess that's it.
Thank you, Maksym. Any questions for Maksym? Okay, thanks again. Up next is Yana.
Yeah, hi. Can you hear me well?
Yeah, can you maybe speak a little louder?
Yeah, I'll try. Maybe now you can hear me well. Better? Is it better now?
Yeah, better. Yeah, it's better.
Okay. Then I'm sharing my screen.
Okay.
And we will start. Yeah, so hello everyone. My name is Yana, and today I'm presenting you my project, Enabling Advanced Network and Infrastructure Alliance. I'm working under the guidance of Sean McKee and Pythia Vasileva, which are both from University of Michigan, and I just joined on the 1st of July to this team. So I'm kind of going to introduce you the overview to the project and my mentors and how my mentors and I envision my contribution to this project. So to begin with, let us have like a very wide perspective of what we are dealing with. Perhaps everyone knows that Large Hadron Collider produce like an enormous amount of data, and in order to use it efficiently, this worldwide LHC computing grid together with the open size grid interconnects almost 1.5 million computer cores among 170 sites from 42 countries. And that's how lots of physicists and scientists can efficiently use this data and have access to this data and like work on their projects and researches. However, of course, in such a large network, it's impossible to avoid problems with the transfer of information, and there can be many reasons for this. For example, fault devices who maintain the performance of the network, or someone is trying to download a huge amount of data and using a lot of traffic and so on. The team I work with has set the task of like taking a comprehensive approach to solve these problems with maintenance of the network and monitoring its performance. So this can be partially solved by creating a notificating software that will inform users about the root of the problem with the network. So first of all, we use the data collected by Personae. It's like measurement agent analyzes the network and helps to gather an information about throughput, about packets which were delivered from one source to another, and it monitors like 6,000 combinations of source destination pairs and runs different tests among them. And then the data with this throughput, the amount of packets which were delivered are stored in Elasticsearch. So let's have a closer look to how the database look like in the Elasticsearch. Here you can see the screenshot from the Elasticsearch, and we can see these heaps, which are kind of result of the tests and provides us with data about what was the destination host, what was the source of our hits, and that's how it looked like. And what is the main idea? Here you can see the scheme of the final product. The final product is the system, alarm, and alerts, which the idea is that user can subscribe to different alerts and alarms and get notifications to their mail about what is happening to the network right now, what are the problems with that, and it helps to decide whether you can do something about that and to improve the network performance. In the backend of that, there's Python code which generates this alarms, and also another subsystem of this is PS dash, that is the web page where the user can see the visualization of these problems and have a description in more details of the problem. So let's see the example of the alarm. This certain alarm is bandwidth decreased on the PS web page, and at the top of the page, the user can see the message with the description of the alarm. In this particular case, the alarm indicates a significant drop in throughput for a link, and the procedure captures multi-site bandwidth degradation. This is an event the site experiences issues in both directions, as a source and as a destination, and from and to multiple other sites. So you can, in more details, look to each of this source and destination point and see the visualization of this problem. So that was just one example. Here you can see the names and short description of other already existing alliance, because the team did this project quite for a while, but the data set is huge, and the amount of this alliance is also significant. Some of them are not implemented yet, and some of them are not even discovered yet. So to get such a line, you first need to write a Python code that finds the desired Python in the data, then add this code to the infrastructure and test that and provide the visualization to this certain alarm for PS dash, and then to align everything that was already done with a new code. That's why here we can see the timeline of my work in this project. Of course, first weeks are just familiarization with what is going on, how Elasticsearch and Kibana, for example, is used in this project, how the code is implemented, how the structure on the GitHub looks like. Next week, I will spend implementing one of the lives and then deploying and debugging it. And another part of this project is to spend 2 to 3 weeks coming up with an idea of another alarm and implementing it as well. Also aligning with the previous alarms, of course, writing the documentation and summarizing the work and evaluating the performance of this alarm. So thank you. That was shortly about the project. And if you have any questions, I'm here to answer.
Thank you, Yana. It's a nice talk for having just started. So seems like you're off to a good start. So, any questions for Yana? Okay, thank you. Next up is Vladyslav.
Yeah, give me a second. I will share my screen. So you should see something.
Yep.
And I will make it bigger.
Okay.
Sorry, it's spoilers. So you see my screen, yeah?
Yeah, you're all
okay.
set.
So hi everyone. I'm Vladyslav Yankovskyi, a master student at the Russian International University of Kyiv. My supervisor is Andriichuk from IRIS-HEP, and my project is devoted to development of the generic vertex finder in HLT1 level trigger at LHCb. So, first of all, what is this HLT or high-level triggers are? So currently the LHCb detector is capable of reading out a maximum data rate of 40 terabits per second, which is a huge amount of data that needs to be filtered, and which is achieved by two software stages, namely HLT1 and HLT2, which have their own tasks for this. So the most interesting for us now that is in LHC run 3, HLT1 was improved by implementing it on a GPU, which allowed for parallel event processing. So this is the first fully GPU-based trigger used for HEP research, which offer unique research opportunities to us. So also in run 3, it became possible to work with a new type of tracks. Previously, in previous runs, long tracks were used for studying, which is left signal in all tracker systems of detector. Now we can reconstruct downstream tracks, which expanded the possibilities for studying long-lived particles, which could escape from valve detector. So now we have a new unique tools, updated HLT1 and U type of tracks, and want to use them for research. So the first is a study of eta-C production on LHCb. So eta-C is a ground state of germanium, which is very interesting for quantum chromodynamics and new physics research. So previously in run 1 and 2, it was actively studied as an intermediate state on the B hadrons decaying. You can see it on the brackets. But more interesting, it's from production in collisions via the proton-antiproton decay channel. So this approach has a problem, such a high background due a huge number of pions and mis-ID tracks. So one way to solve this, it's just change the channel and choose one with the long-lived particles. For example, the lambda anti-lambda. Because they doesn't have such a background, such a big background from the pions and this mis-ID. So now it's possible to reconstruct downstream tracks, and since lambda baryons are long-lived, this will improve the efficiency for their detection. Also, we can use both unwound long and downstream tracks with their own characteristics to improve the final results. For example, long tracks has higher reconstruction accuracy, and downstream tracks, we expected that they will provide us more statistics for research. So the second part of the project is devoted to reconstruction generic displaced vertices. So if you're talking about linear physics and models, many of them possess the existence of new long-lived particles that could help explain us some new information about the mysterious in physics, such, for example, dark matter. So, and it's possible that these particles are produced in proton-proton collisions at LHC and can be detected by LHCb. So, however, to do this effectively, to detection, we require a special algorithm that quickly identifies the displaced vertices where these particles appear. Once this algorithm is developed, it will need a fast CUDA implementation to run online on a LHCb GPU farm. So thus, the main goal of the project is the first development of selection algorithm for events with the formation of lambda and lambda pairs using long tracks, downstream tracks, and maybe we think about some combination of this. One lambda downstream and one lambda along. So, and the second part is development of a new algorithm that looks for these displaced vertices and make this implementation on CUDA. So, thank you for your attention. You may ask any questions.
Thank you, Vladyslav. Any questions for Vladyslav? All right, thanks again. Up next is Oleksii. Sorry, Oleksii.
Yes, I'm here.
Yep.
Yes, can you see my screen?
Yep, yes.
Okay, so greetings. I'm Oleksii Hrechykha, a master student in applied physics at Kyiv Academic University. This summer, I will be improving Python's ragged array library under the supervision of Yana Osborne and Jim Pivarsky of Princeton University. The motivation of the problem is rather straightforward. So, as everyone knows, Python is currently the most popular programming language and is also the most widely used in data science. However, because of Python being non-compiled, its calculations are inefficient, and data scientists must employ specific libraries that help solve their problems and do it very fast. And one of such problems in high energy physics specifically is working with ragged arrays, which are arrays of different lengths, which arise when a specific particle does not have the same amount of data from an experiment as another particle we may be comparing it to. And to solve this problem, an awkward library was developed. It allows for arbitrary data structures and works with ragged arrays a lot faster than regular Python does. So you can say that it's similar to its performance boost is similar to what NumPy does compared to working with lists with Python without employing specific libraries. And so Awkward uses NumPy, but however, there is a problem with using lots of different libraries which which allow the user to work with arrays, and that is the issue of standardization, because essentially the more libraries you have, the more they start diverging from each other, and to combat that, this fragmentation of array library ecosystem, certain standards have been developed by the community, which are based on NumPy, but also general enough for other libraries to employ them. It means is that libraries such as NumPy, TensorFlow, PyTorch, CuPy, etc., are all generally interoperable. And the problem with Awkward is that due to it allowing arbitrary data structures, it cannot employ or rather fulfill the obligations which API places on it. And in order to combat that, a ragged array library is being developed, and it is basically a wrap around Awkward, which somewhat limits its usage, but allows the user of the ragged library to work with ragged or jagged arrays in an AP complacent way. And the API specification has states that every library must employ certain functions which are act in predictable ways. And this is implementation of such functions, or rather those functions that haven't been yet implemented, is what I'm doing in this project. So functions that do basic linear algebra, work with sets, do indexing, etc. This is what I will be doing. And currently, we can take this function as an example. This is what I work on. This function must return the unique elements of an input array, and it's one of a branch in a number of functions which deal with uniqueness of elements in an array, and then they combine into one large function which has multiple parameters in it, let's say. And as I am a beginner in Python, so far I have understood what this function should do, wrote an algorithm for which does what the API says such function should do. And I've also looked into writing tests, measuring calculations time to judge the efficiency of the function, etc. Currently, I'm focused on improving the algorithm we have, and later on, once the algorithm for a function is good enough, we will be implementing NumPy, or I'm sorry, Numba in the function to speed up the processes. And also the general idea is that we should employ, say, awkward library as much as possible, because it has many functions implemented already. And since they work very fast, we can sort the array or flatten the array, so make it one-dimensional in a very efficient manner. And that's what I will be focusing on going further. Thank you for your attention. If there are any questions, I will be happy to answer them.
All right. Thank you. Any questions for Oleksii? Okay. Next up is Artem.
Yep, sure. With pleasure. Second, have some problem. Yep. Do you see my screen?
Yeah, we can see it.
Okay, super. My name is Artem Havryliuk, and today I'm gonna tell you about my project. But before I start, I want to express my deep gratitude to IRIS-HEP, to my mentors, Jim Pivarsky and Philip James Ilton, to my home university, KAU, and especially many thanks to Robert, who has been communicating and supporting the participants for many years now, because it's my third time with IRIS-HEP, and I know what I'm talking about. So thank you, Robert. The topic of my project is array-oriented Python interface for the Pythia event generator, and we need to understand what is Pythia and what is the problem with it. The Pythia event generator is a sophisticated open source software tool used primarily in high energy physics to simulate the outcomes of particle collisions, such as those that occur in particle accelerators, like the Large Hadron Collider This event generator plays a crucial role in theoretical and experimental physics by providing detailed simulations of particle interactions, which helps physicists to compare their experimental results with theoretical simulations, which is very helpful, actually, and to develop new theories about the fundamental forces of nature. It's primarily written in Fortran and C++. It has Python interface, but it has some limitations. So what's the problem? The primary issue with Pythia's current Python interface revolve around inefficiencies in processing large datasets, limitations of Python's iterative capabilities, like complexity in handling nested data structures, scalability challenges, interfacing overheads, and reduced usability in interactive environments such as Jupyter Notebook, which is very helpful. And these problems collectively hinder the ability to perform high throughput, large-scale simulations, which is necessary to cutting-edge research in particle physics. So, and our plans, our comprehensive plan to enhance Pythia involves developing an array-oriented Python interface that significantly, we hope, improves performance and usability for large-scale simulations. And we plan to do it by leveraging the awkward array library and optimizing memory management and ensuring seamless integration with Pythia's C++ core. And we aim to create a robust and efficient interface. And we hope that extensive testing, comprehensive documentation, and community engagement will ensure that the new interface meets the needs of the particle physics research community and facilitates high throughput productive level simulations. So that's generally it. We hope that we'll do it and everything will be great. So that's it.
Thank you, Artem. Any questions for Artem? All right, thank you. Next up is Yurii.
Yes, hello.
Yep.
Okay, I'm sharing my screen. Can you see it?
Yep.
Okay, I turn on my camera. Okay, hello everyone. My name is Yurii Perets. I am a Kyiv National University student. I am working on the project CI/CD improvements for Alpaka library and related projects. My mentors is Volodymyr Vezguba and Irzy Vyskochil. So first of all, we need to start with problematic. Why do we even need Alpaka library and how it occurred? We will start our introduction from high-energy physics experiments, because high-energy physics is facing an enormous challenge in the coming decades as data volumes and processing requirements for precision physics analysis increased, especially with next generation experiments like deep underground neutrino experiments and high luminosity large hadron collider experiments. One of the way to fix it is to proceed computation not just on the CPUs, but also on the GPUs. And the most effective way to do it is by heterogeneous computing, which is when in our system we have few subsystems which can have different architectures. So it's it's our key to meet the computing challenge. But there is also a problem. Programming technique for GPUs and those are parallel accelerators very different from that of traditional CPUs. So each of them have its own language, and to write code, you need to understand hardware architecture. And there's a problem because of the over last decades of high energy physics experiments have developed million lines of code, And in order to use these new computational accelerator facilities, you would need to rewrite large amount of their code bases. To be able to run on all the different hardware architectures. And this task should be repeated multiple times in each architecture's preferred language, so it would be very time consuming and expensive. So we need some solution so we could run our code on one machine and proceed it on all the others. And this solution is Alpaka library. So firstly, we start with an overview of parallelization of data in Alpaka library. Each parallelization level corresponds to a particular memory level. Our blocks of grids corresponds for global memory. Our grids corresponds for global memory, blocks for shared memory, and threads for register memory. Grid is n-dimensional set of blocks with a usually large global memory accessible with all threads in all blocks. And grids are independent of each other. Those can be executed either sequentially or parallel. Same for the blocks. It's an in-dimensional set of threads with high bandwidth, low latency, but small amount of shared memory. They are independent between each other and can be executed sequentially or in parallel. Threads is the execution of sequence of instructions. So now we need to talk what is the point of our project. What are we doing? So our project aims to optimize the test coverage and runtime of Alpaka. Because firstly, if we configure all of the possible software dependencies, all of the possible architecture dependencies, it will result in about 2,500,000 different combination of test jobs. If we assume that each job would take like 4 minutes, it could take 4 months. So after implementing an open source CI job generator that was written in Python and works using pairwise testing, which is for combinational software tests, the generator reduced number of jobs to about 117. But there is also a problem that we don't know if all the possible number of jobs was generated. So as a result of the project, we want to finalize the work on the new open source version of the generator, migrate Alpaka to the new generator, and verify that the CI works as expected. Thank you for your attention. Any questions?
Thank you, Yurii. Any questions for Yurii? No, thank you. Thanks to all the fellows for your talks today. They all seem very interesting. Thank you for everybody else for showing up to listen to their talks. And that's it for today. So thank you.
Thanks, everyone.
Thank you very much.
Thank you. Goodbye.
Bye. Thanks.
Goodbye.